Moving on to number 42, and with this we're going to move into forced oscillations and resonance. Number 42 states the following. How much energy must the shock absorber of a 1200 kilogram car dissipate in order to dampen the bounce that initially has a velocity of 8.8 meters per second at the equilibrium position? So V is 0.800 meters per second, and M is equal to 1200 kilograms. And the question is, how much energy must it dissipate? Well, all of the energy here is described as kinetic energy, and that's going to equal 1/2 mv squared. This is going to equal 1/2 times 1200 times 0.8 squared. If you do the math here, you get 384 joules. So you have to dissipate 384 joules of energy in order to eliminate the energy that's generated with this situation. Number 45 states, suppose you have a 0.75 kilogram object, 0.750 kilogram object, on a horizontal surface connected to a spring that has a force constant of 150. So K is equal to 150 newtons per meter. And the simple friction between the object and the surface is a coefficient. So the coefficient of static friction is 0.100. The question is, and this is the kind of question that I actually like, is how far can the string be stretched without moving the mass? So first of all, we have to calculate the friction force here. And we know that the friction force is equal to the static constant times the force normal, which in this case, because it's horizontal, it's going to equal to its weight. And so that's going to equal 0.1 times the mass, which is 0.750, times 9.8. And so the friction force here is going to equal 0.3735 newtons. 0.735 newtons. Okay. So basically the question is now, if we go to the force, elastic force, and we set that equal to the friction force, because that's the maximum point of stretch, this is going to equal minus kx, okay? And so if we put that in, that means that x is going to equal this elastic force, which is now the friction force. So it's going to equal to the friction force divided by k. And that's going to equal to 0.735 divided by 150. And if we do the math there, we get 4.9 times 10 to the minus 3 meters. So it will stretch that many meters, or 0.49 centimeters. So about a half a centimeter. It stretches about a half a centimeter before it starts moving. So that's A. The second question is, if the object is set into oscillation with an amplitude twice the distance that found in part A, and the kinetic coefficient of friction is 0.085, what is the total distance does it travel before stopping? Now, in order to do this, basically there's a example in the book that you have to look at that's very similar to this, and it's example 16.7. I had to look back because there's no problem or formula given just in the various formulas, and I'm not necessarily suggesting that you remember this formula, but you can write it on your 3x5 card if you want to. And so the distance from this example problem, the distance is equal to is equal to 1/2 times k times x squared, and it says twice as far, so that we had a 2 there, divided by mu k times mg. Now, if you want to see where all that came from, you can look at how they went through this in this example problem. I am not going to do that here. So that's going to equal 1/2 times 150 times 4.9 times 10 to the minus 3 from the previous problem times 2, as it says, divided by 0.085, which was what was given in the problem, times 750 times 9.8. And if you do all that math and crunch it, you get the distance traveled is 1.15 times 10 to the minus 3 meters, or 0.115 centimeters. So not very far, really. The next problem is problem number 48. And with problem number 48, let's see, we can't see it on this thing because I have to roll this up a little bit. We're moving into waves, okay? And waves, key formulas, you already know that t, which is the period, is 1 over f, which is the frequency. But another key formula is the velocity of a wave is equal to its wavelength, which is the distance from one peak to one peak of a transverse wave, or from one trough to one trough, and it's equal to that wavelength times the frequency. And you want to remember that. That's a formula you want to keep in hand. So the next problem is problem number 48. Waves in a swimming pool propagate at a velocity of 0.750 meters per second. So they give you the velocity of this wave. You splash the water at one end of the pool and observe the wave go to the opposite end, reflect and return in 30 seconds. So t is equal to 30 seconds. How far away is the other end of the pool? Okay, this is really a velocity problem. Velocity, or distance, is equal to velocity times time, which is equal to, so the distance here is going to be 0.750 times 30, which is 22.5 meters. Now that's up and back, so you divide that by 2, and it's 11.25 meters to the other end, which is what the question is. How far is it to the other end of the pool? The next problem is problem number 51. Problem number 51 states, scouts at a camp shake a rope bridge they have just crossed and observe the wave crests to be 8 meters apart. Now what they're telling you by saying that, they're telling you that the amplitude, or the wavelength, so the distance from one amplitude to the next is 8 meters. And that's what they're telling you with that statement. If they shake the bridge twice per second, so they're telling you again the frequency is 2 hertz, or 2 per second. And they're asking what is the speed? Well, the speed, velocity, is equal to wavelength times frequency, which is equal to 8 times 2, or 16 meters per second. Very simple. Number 55. Number 55 says, your ear is capable of differentiating sounds that arrive at the ear just 1 millisecond apart, so 0.001 seconds apart, 1 millisecond. What is the minimum distance between two speakers that produce sounds that arrive noticeably different times of the day when the speed of sound is 340 meters per second? Okay, they're telling you that so distance is equal to the velocity times the time. And so they're saying you can detect this amount of time separated. So how far apart they would have to be is equal to that time times the velocity of sound. So that's going to be equal to 0.34 meters apart. 0.34 meters apart, or 34 centimeters. Number 57. Now with 57, we start talking about interference and superimposition, and we talk about the concept of beat frequency. Now the beat frequency is something that occurs when two waves run into each other and they have a very close frequency to each other. And the beat frequency is the frequency of one minus the frequency of the other, the absolute value of that, okay? And you can only hear beats when these two frequencies are very close together. And musicians use this phenomenon in order to tune their guitar. If you have two notes that are supposed to have the same frequency, if they're very close but they're not the same, you can hear the beats of sound, or the frequency of the beats of sound, and you can try this on a guitar sometime. So this first problem states two car horns, one emits a frequency of 199 and the other emits a frequency of 203. What is the beat frequency? Well, the beat frequency will be the subtraction of these two, or 4 hertz. So you'll hear an overriding sound that has a frequency. Number 58. Number 58 states the middle C hammer of a piano has 2 strings producing beats, a beat frequency of 1.5 hertz. One of the strings is tuned to 260, and it's asking what frequencies could the other string have? Well, it can either be 261.5 or 258.5, such that if you subtract, remember it's the absolute value, so it can either be 1.5 larger or 1.5 smaller. Number 59. With number 59, you have two tuning forks having a frequency of 460. So F1 is 460 and F2 is 464 hertz. They're struck simultaneously. What is the average frequency? Well, the average is just how you would think it. You add F1 and F2 and divide by 2. So you get 460 plus 464 divided by 2, and so the average is 462. And then the beats frequency is going to be the subtraction of these two, which is going to again be 4 hertz. 63. Now with 63, we're moving into intensity. And the key formula here is I is equal to power in watts over area. So the intensity is the power in watts per unit of area. And number 63 states ultrasound intensity is 1.50 times 10 to the second watts per meter squared. It's produced by a triangular head that measures 3 by 5 centimeters, or 0.03 by 0.05 meters. That's very important to change that into meters. What is the power output? Well, the area here is going to equal 0.0015 meters. So if you rearrange this, I times A is equal to P is equal to 1.5 times 10 to the second times 0.0015, and that's going to be 0.225 watts. So that's the power output for this ultrasound. Number 64. We're almost finished. Number 64 states, the low frequency speaker stereo set has a surface area of 0.05 meters squared and produces a power of 1 watt. What is the intensity of the speaker? Well, the intensity is equal to P over A is equal to 1 divided by 0.05, which is equal to 20 watts per meter squared. The second question is the speaker projects sound uniformly in all directions. At what distance is the intensity 0.1 watts per meter squared? So if you start like this, it's a sphere, and that's important to realize it's a sphere. And it's asking what the radius of that sphere is. Well, the surface area of a sphere is 4 pi r squared. And so the question is, if you have a sphere like this, the area is going to equal power, which is 1.0 watts, divided by an intensity, which is now 1.1 watts per meter squared. So the area has to be 10 meters squared. Then you put this into this formula and find r, and that tells you the distance. So if 4 pi r squared is equal to 10, if you do the math, r is going to end up equaling 0.89 meters. 66. Well, we're just going to press on. This one's a little bit longer than most of my videos, but we're going to press on because we only have a few more to do. 66 states, a device called an isolation meter is used to measure the intensity of sunlight at an area of 100 centimeters squared and registers power of 6.5 watts. What is the intensity? Well, I is going to be P over A, which is equal to 6.5 divided by, not divided by 100. You have to divide this by 100 again to get it in meters, okay? So it's going to be divided by 0.01 meters squared. And if you do that math, you get 650 watts per meter squared. It states a photovoltaic array is 10% efficient in gathering solar energy and converting it into electricity. If the average intensity of sunlight in one day is 700 watts per meter squared, what should your array have to gather energy at a rate of 100 watts? Okay, so this is the intensity, this is the power, and you have a 10% efficiency. It wants to know what area do you need to get what you want out of this. Remember that I is equal to P over A, so A is equal to P over I. And if it were 100% efficient, you would just put 100 divided by 700. But it's only 10% efficient, so you have to multiply that by 10. And if you do all that, you get 1.43 square meters. Now the second part of this problem states, What is the maximum cost of the array if it must pay for itself in 2 years? Averaging 10 hours a day. Okay, so 2 years, 10 hours a day. There are 365 days in a year, 25 days in a year. And you're going to do measuring in kilowatt hours, so you're going to stop right there. So if you start with that and multiply it out, you get 7,305 hours. If you take 100 watts, which is what your power is, that's 0.1 kilowatts. And you multiply that by your 7,305 hours, that gives you 730.5 kilowatt hours. And at 9 cents per kilowatt hour, that's $65.70. So if you're going to get paid back in 2 years, it has to cost $65.70. The last problem is problem number 70. Problem number 70 states that a microphone receiving pure sound tone feeds an oscilloscope, producing a wave on the screen. If the sound intensity is originally 2.00 times 10 to the minus 5 watts per meter squared, but is turned up until the amplitude is increased by 30%, what is the new intensity? Now we know from reading the book, we know that intensity is proportional to the square of the distance, amplitude. In other words, if you change the intensity by a certain amount, you change the amplitude by the square of that amount. So that means that a higher intensity divided by the lower intensity, the original intensity, is going to equal the new amplitude. And so you want to know what this is. You've got 1.3 over 1 is equal to this. So I2 is going to equal to 2.00 times 10 to the minus 5 times 1.3 over 1 squared. Do the math and you get 3.38 times 10 to the 5th minus 5 watts per meter squared.